The standard deviation is another measure of variability or spread for a set of data, but it's measured based on the mean. So when we find that arithmetic center, then we start measuring how far each data point is away from the mean to find out what that standard deviation is. So it's a little bit more dependent on the data, and it measures each data point's distance from the mean. And so we like this measure a lot more than we like range, because it's like how the mean is a little bit better measure of center than the median, because the median's just counting down. And in this case, the standard deviation is a little bit better because it's looking at every data point, how far is it from the mean. And to do this, we have two variables that we use. One of them is sigma. This is what we call sigma. And it's a lowercase sigma, and it is the population standard deviation. And S is the sample standard deviation. Down here you can see that's sample. So we have a crazy formula, but I will show you how to do this on the calculator as well. But I want to work through the formula once or twice just so we can see how it works out. And when you look at this, we're looking at the sum of each data point's distance from the mean, like I was telling you. So we're going to take each data point, subtract off the mean, and then we're going to square it. And when we square it, that allows us to always get a positive number. Because if the data point's smaller than the mean and you do, say, 3 minus 5, you're going to get a negative number. But if we square it, we'll get a positive every time. And then we add all those up, and then we divide by how many data points we have in our data set, and then we take the square root of it to undo this squared that we introduced here, and that gives us our sigma. So this is the sum of each data point minus the mean, and then you're going to have the each data point minus the mean is going to be squared. Okay, so that's the process there. Mu is the population mean, remember? X bar is the sample mean. And notice here we're using the distance from mu when we're trying to find the population standard deviation. And here we're using the distance from X bar when we're trying to find the sample standard deviation. That makes sense. We're also dividing by the population size here. And here on the sample standard deviation, we're dividing by the sample size, but we're taking away 1. And that's because it's a sample, and we don't want to give it quite as good an estimate because it is sample data and it's never going to be exactly the same as what the population standard deviation is. So we kind of give a fudge factor in there. So x sub 1, that x sub I, that's a data point, or each data point from our sample or from our population. Capital N is the population size, and little n is the sample size. So these two formulas you don't have to memorize, but you do have to write them and use them correctly. The summation of the distance of each data point from the mean squared, and then add them up, and then divide by the population size, and then take the square root of the whole thing. If you're doing it for a sample, you're finding still the distance from each data point to the mean squared, and then add all those squared differences up, and then divide by n minus 1, which is the sample size minus 1, and then take the square root of it. Not too hard when we write it with a table, and so I'm going to show you how we like to do that. Here is our data set. We have 1, 2, 3, 4, 5 items. So it is, here we say it is a sample that we have, and so our n, our small n, is 5. First thing that I like to do is list out all of the data points in the data set, and then I want to subtract each one, subtract off the mean. Well, first I have to find the mean. I don't know what the mean is, so to find the mean, I'm finding x bar, of course. I'll have to add each of those. 2 plus 5 plus -1 plus 10 plus 1 divided by my n, which is 5. 1, 2, 3, 4, 5, yeah. my negative 1 and 1 are going to cancel. I think it's going to be 17 divided by 5, so it's going to be a little over 3. But let's try it out and see what we get with the calculator. So here I have 2 plus 5 plus negative 1. You can use this button to give you negative, plus 10 plus 1 equals 17, and then divide that by 5. 3.4. So my mean is 3.4. And I need to use that here. Instead of this x bar, that should be 3.4. Okay, and then first thing, I have all my x sub i's written down, which are just each of my data points. And then I will take, my formula says to subtract the data point minus the mean. So I will do negative 1 minus 3.4, and I'll get negative 4.4 because of the negative on the 1. And then I have 1 for my next data point, so it'll be 1 minus 3.4. And so let's just do that real quick. 1 minus 3.4. I get negative 2.4. And 2 minus 3.4. That should be negative 1.4. 5 minus 3.4. That should be 1.6, I think. Let's try it out. 5 minus 3.4. 1.6. And then 10 minus 3.4, I think should be 6.6. It says the summation of the x's, like I need to add all those up. Well, I already did that. Remember, we got 17. And then we did already find the mean. I did that up above, so we can put in the 3.4. And then here we are subtracting off that 3.4. I need to square them first. So that's the next thing in my formula. It says do that whole subtraction and then square it. So here we're doing negative 4.4 quantity squared, negative 2.4 quantity squared, negative 1.4 quantity squared, 1.6 squared, and 6.6 squared. So I'll type each of those in, negative 4.4, and I have a square. So if I put that negative 4.4 inside the parentheses, because I'm squaring the entire quantity, and then push equals, I'll get 19.36. And I really do expect all my negatives for my differences to come out positive on the right after I square, because I'm doing negative times negative, and that's always a positive. So I do expect the 2.4 squared to be a positive number, so I don't have to go through putting in the parentheses and the negatives, but I get a positive 5.76. Do it with 1.4. I get 1.96, 1.6, and 6.6. I have no idea, so we'll square that. I get 43.56. Now at this point, my formula says I have this quantity squared, and then I'm going to need the summation of it. If we slide up just a hair, we can see what we've done so far is found the difference from each data point to the mean and squared it, and now we have to sum that up. Then we will divide by our n, and then we will take a square root. And I might be on the wrong formula here, because this is a sample, yeah, so I was on the wrong formula. All right, so let's add those up. 19.36 plus 5.76 plus 1.96 plus 2.56 plus 43.56, and I get 73.2. Now we have space here to write out the formula because I have just the numerator calculated, so I want to rewrite that formula. Remember, it is for a sample. So I'm finding the sample standard deviation, and it's going to be the giant square root, the summation of each x sub I minus the x bar that we came up with, square them, and then finally do the sum over n minus 1, because we are looking for a sample. So when I plug in my values, still the giant square root, but instead of that whole numerator part, I calculated 73.2. And my n is 5, so I take away 1, and that leaves me dividing by 4. So 73.2 is still sitting on my calculator. I can just do divide by 4 equals, and I get 18.3. I do need the square root still of 18.3. And to do a square root, I will just do second and that x squared button that we found. You see the square root above it? So I'll click there. And then I can take the answer I had before, or I can retype it, but I prefer to take the answer so I don't lose any decimals. Put the right parenthesis, equals, and I get my S, my sample standard deviation is 4.2778. And I could put another digit after, it would have to round, but I'm going to look at that 4 and not bump up my 8. So I'm going to leave it at the 2778.